Hello everybody, I will make a summary about the main topics in the chapter 1, which is atom, before the exam. As we all know, in a neutral atom we have number of proton equal to number of electrons, which is equal to the atomic number, while the mass number is equal to the number of a nucleon. Number of a nucleon is equal to the number of particles inside the nucleus, which these particles are protons and neutrons. So A equals Z plus N, and we can find number of neutrons as in this form, N equal A minus Z. The chemical representation of an atom is represented as X, A, and atomic number Z, so it is represented by these two numbers A and Z. For example, if I'm having 14 nucleon, this means that its mass number is equal to 40, and its atomic number is half its mass number. Atomic number is half its mass number. Z equal mass number over 2, since it is half. How can we determine its composition? Its composition, we need to find number of protons, number of electrons, and number of neutrons. Since atomic number equal A over 2, so it is equal to 40 over 2, it is equal to 20. So from the atomic number, I find number of protons, and you can find number of electrons, so they are equal to 20. We still have number of neutrons. Number of neutrons equal A minus Z equal to 40 minus 20, it is equal to 20. So by this way we can determine the particles present in this atom, which are protons, electrons, and neutrons. To calculate the charge of a nucleus in a certain atom, charge of a nucleus is equal to plus ZE. According to the rule, charge of a nucleus equal charge of protons plus charge of neutrons. But the charge of a neutron is equal to 0, since neutrons are zero charged. So charge of proton equal number of protons times the charge of one proton. And the number of a proton is equal to atomic number equal to Z. Charge of a proton equal plus E. E is always given in the exercise, so we get plus ZE. For the charge of electron, similarly, charge of electrons equal number of electrons times the charge of one electron. Number of electron is also equal to the atomic number in a neutral atom, and charge of electron is negative, so it is equal to minus ZE, and E is given 1.6 times 10 to power minus 19 coulomb, and coulomb is the charge of electron. Atom is neutral since the charge of the atom is equal to the charge of a nucleus plus a charge of electrons. It is equal to plus ZE minus ZE, it is equal to 0, so atom is electrically neutral. To get the atomic mass, the rule is atomic mass equal A, which is mass number times mass of a nucleon, where mass of a nucleus is equal to 1.67 times 10 to power minus 27 kilogram. For example, if we have atom calcium with mass number equal 40 and atomic number equal 20, we can calculate the charge of the nucleus of this atom according to the rule plus ZE, and it is equal 20 times 1.6 times 10 to power minus 19 coulomb, and we can calculate its atomic mass equal A times 1.67 times 10 to power minus 27, and we get the answer. With respect to isotopes, the difference between isotopes is their mass number and their number of neutrons, but they have same atomic number. For example, magnesium exists in nature in the form of 3 isotopes, Mg24, Mg25, Mg26. The mass number is different. Each isotope has a different percentage relative abundance. In this example, magnesium, which has percentage 79%, is the most abundant isotope, while the heaviest isotope is the isotope with a higher number or higher mass number. It is Mg26 with percentage 11. To calculate average atomic mass of these isotopes, the rule is percentage of the first isotope times its mass number, plus a percentage of the second isotope times its mass number, percentage of the third isotope times its mass number, over 100. If we have two isotopes, we use only two values. If we have four isotopes, it is the same. It is a percentage times mass number over 100, and by calculation we can get the average atomic mass in A and U. Atoms are arranged in the periodic table in different rows and columns. The periodic table has 7 rows and it is formed of 18 columns. The atoms are arranged in an increasing order of their atomic number. To know the correct position of any atom in the periodic table, we have first to make electron configuration. Electron configuration depends on the number of electrons, and the number of electrons are equal to atomic number, so we depend on that to make electron configuration. By writing the electron configuration, we can find the column and the row of this element, and so we can determine its location in the periodic table. How can we make electron configuration for a certain atom? In order to make correct electron configuration, we have first to write this diagram: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. S, P, and D and F are the sub-levels. Each sub-level is filled by a certain number of electrons. For example, level S is filled by 2 electrons. Level P is filled by 6 electrons. Level or sub-level D is filled by 10 electrons, and sub-level F is filled by 14 electrons. The row 5 contains 5s2, 5p6, 5d10, 5f14. Also we have 6s2, 6p6, 6d10, we start by 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14 till 7s2, 5f14 for 7p6. This is the correct electron configuration. For example, if we start by any atom named X, which has atomic number equal 12, so the number of electrons is equal to 12. We start by 1. We have 12 electrons to be distributed correctly on the energy level. We have 1s2, 2s2, 2p6, 3s2. By adding the number of electrons, 1s2, 2 electrons, 2 electrons, and 6 and 2, we get 12. So the number of electrons equal 12, and this is a correct electron configuration. For atom Y, for example, if its atomic number is equal to 32, start by 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Till 3d10 we have 30 electrons, then 4p2. Then for 3d10 we have a 30 electron, and the atomic number is 32. We still have 2 electrons. 2 electrons is on sub-level P. Since it can be filled by 6 electrons, the maximum number of electrons is 6, so we can put 2 electrons on P. For atom Z, which has atomic number equal to 26, also 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, we have 3d10. Since for 4s2 the number of electrons is equal to 20, but its atomic number is 26, we still have 6 electrons. We can put these 6 electrons on D. Since it can be filled by maximum number of electrons, which is 10, we can put 6 on it. How can we determine the row and the column of a certain element? Row is the highest energy level. For example, in atom X, highest energy level is 3, so its row is 3. For atom Y, the highest energy level is 4, so its row is 4. For atom Z, the highest energy level is 4. It is not the last energy level, it is the highest energy level. So its rho is 4. To determine the column, first it is the number of electrons on the outer energy level. If electron configuration ends by S, take the number of electrons on S. As in example 1 for X, the electron configuration ends by S2. So we have 2 electrons on S. Its column is equal to 2. For atom Y, the electron configuration ends by P. And the rule says if the number of electrons ends by P, take the number of electrons on P and add 12. On P for atom Y, we have 2 electrons. So we add 2 plus 12 to get 14. So it is in column 14. For element Z, the electron configuration ends by D. When electron configuration ends by D, take the number of electrons on D and add 2. So it is in column 8. For elements where electron configuration ends by F, it ends by 4F, it is called lanthanide. And if their electron configuration ends by 5F, they are called actinides. We are not asked to determine the column of elements where electron configuration ends by F. To determine the families of the elements, we have 4 important families. The first family is the alkali metal. Alkali metal are the elements that exist in column 1. So their electron configuration end by S1 and their valence electron is equal to 1, where valence electron equal number of electrons on the outer energy level. If electron configuration ends by S, valence electron equal number of electrons on S. If electron configuration ends by P, valence electron equal number of electrons on P plus 2. For alkali metal, they start in row 2, since in the first row we have hydrogen, and hydrogen is not metal, so the alkali metal start in row 2. For alkaline earth metal, these are the elements that exist in column 2. Their electron configuration should end by S2 and the valence electron is equal to 2. For halogens, they are elements in column 17, so their electron configuration ends by P5 and they start also in row 2. For inert gases or noble gases, these are the elements that exist in column 18, where electron configuration should end by P6, but they start in row 1 and the valence electron is equal to 8. Let's take an example. If we are asked to make electron configuration for the second noble gas, first noble gas is in column 18. Second noble gas, we know that noble gas start in row 1, so the second noble gas is in row 2. According to this information, we can make electron configuration 1s2, 2s2, 2p, so we are in row 2, and column 18 we should stop at p6, so 2p6. Atomic number in this case is equal to the number of electrons. 6 plus 2 plus 2, it is equal to 10. For the third alkali metal, it is in column 1. It is in column 1. But the third alkali metal, since the elements in column 1 start in row 2, so the third alkali metal is in row 4. From the column and the row, we can write electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. We are in row 3 now. 4s2, we are in row 4, but we should stop at s1 since it is in column 1. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. By adding the number of electrons, we get that the number of electrons equal to atomic number equal to 10 plus 8 equal to 19. Some rules which are needed for calculation to calculate the number of mole or the mass or the number of atoms of a certain atom. We have these two rules. Number of mole is equal to mass over molar mass. So if we need to find mass, we can multiply number of mole by molar mass. Also, we have number of mole is equal to the number of atoms over Na. Na is the Avogadro's number, which is given in the exercise. And if we have to calculate the number of atoms, we can multiply number of moles times Avogadro's number. Let's take an example. For example, if we have calcium with atomic number and mass number, suppose you have the mass of this calcium atom is equal to 0.4 gram. To calculate its number of mole, we can say that number of mole equal mass over molar mass. So 0.4 gram molar mass is equal to A over 40 gram per mole. The unit of molar mass is very important. It is gram per mole. By calculation, we get 0.01 mole. This is the number of mole of calcium atom in 0.4 gram. If we have to calculate the number of atoms present in this quantity, we have number of mole is equal to number of atoms over Avogadro's number. So the number of atoms equal N times Avogadro's number. N is calculated above 0.01. Avogadro's number is 6.023 times 10 to the power 23. By calculation, we get 6.023 times 10 to the power 21 atoms. Let's make some application about the rules explained before. We have in this table 4 atoms with different properties. Let's start by atom copper. Atom copper has electron configuration which ends by 3d9. So by making electron configuration for copper, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. We stop with the 3d9. With respect to element K, which is potassium, it is the third alkali metal. Since it is the third alkali metal, so it is in column 1, and we know that the elements in column 1 start in the row 2, so the third alkali metal is in row 4. By making or by writing electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4, this is row 4, but in column 1 we stop at 4s1. To determine the location of copper in the periodic table, the electron configuration of copper ends by d9, so its column is equal to 9 plus 2. We take the number of electrons on d and we add 2. It is in column 11. For row, it is in row 4, since the highest energy level is 4. To calculate the mass number of zinc, the given was atomic mass. Atomic mass is equal to A times mass of a nucleon. So A is equal to atomic mass 108.55 times 10 to the power minus 27 kilogram over mass of a nucleon, which is always given. It is 1.67 times 10 to the power minus 27 kilogram. The answer is 65. To deduce the molar mass is equal to A, but its unit is gram per mole, so it is 65 gram per mole. Part 4, we have to specify the composition of argon and write its chemical representation. For argon, we have a nuclear charge of a nucleus equal plus Ze. So its atomic mass equal atomic number is equal to charge of a nucleus over E. Charge of a nucleus equal to 8.28 times 10 to the power minus 19, and E is given. It is 1.6 times 10 to the power minus 19. By calculation, we get 18. This is the atomic number. And we have another given, that the ratio of the atomic number to mass number, ratio of atomic number Z over mass number, which is A, equals 0.45. So A equal Z over 0.45 equal 18 over 0.45. It is equal to 40. From the atomic number, we can determine the number of protons and the number of electrons, since in a neutral atom, number of protons equal to the number of electrons. Since we have A and Z, we can find number of neutrons. N equal A minus Z is equal 40 minus 18, and we calculate the number of neutrons. In this case, we can find the number of protons, number of electrons, and the number of neutrons of argon atom. In chemistry, we have sometimes mixture of solids. Mixture of solid is called alloy. In this example, we have alloy which is named brass. This alloy is formed of copper and zinc, certain quantity of copper and certain quantity of zinc. In this given, we have zinc, X atoms of zinc, and a certain mass of copper. The total mass of this alloy is equal to 150 grams. And it is also given that the percentage of copper in this alloy is 70%. So, since the percentage by mass of copper is given, the rule is percentage by mass equal mass of copper over mass total times 100. Percentage by mass is 70. Mass of copper is unknown. Mass total is 150 times 100. By calculation, we can get that the mass of copper equal 105 grams. Mass of zinc can be deduced since mass of zinc plus mass of copper is equal to the mass total. Mass of zinc plus mass of copper equal 150. So, mass of zinc equal 150 minus 105, it is equal 45 grams. How can we calculate the number of atoms of zinc present in this alloy? We have a mass of zinc is calculated, it is equal to 45 grams. According to the rule, number of mole equal mass over molar mass equal number of atoms over Avogadro's number. Number of atoms is unknown. Avogadro's number is given. Molar mass is calculated before. Mass is calculated here, it is 45. So substitute 45. Molar mass of zinc, it is calculated in the above part, it is equal to 65 gram per mole. Number of atoms is to be calculated. Avogadro's number is given in the exercise 6.023 times 10 to power 23. By calculation, we can get that number of atoms is equal to 4.169 times 10 to power 23 atom. Don't forget the unit, please. Another given. This time is about silicon. Silicon is an atom with 4 valence electrons. And we know that valence electron equal number of electrons on the outer energy level on the last shell. So, since silicon is has 4 valence electrons, this means that it is in column 14. The lowest dot symbol of silicon is Si with 4 valence electrons. We have 4 dots. It is written in this form. To find the atomic number of silicon, it is below carbon in the periodic table. If carbon is here, so silicon is below it. They are in the same column. For carbon, its electron configuration 1s2, 2s2, 2p2. So it is in row 2 and it is in column. Since it ends by P at 12, it is in column 14. Carbon is in row 2, so silicon is in row 3. Si is in row 3 and it is in column 14. Let's deduce the electron configuration 1s2, 2s2, 2p6, 3, it is row 3, 3s2, 3p2. Since it is in column 14, its electron configuration should end by P2. By adding the number of electrons, Z equal 2 plus 2 plus 6, 10, 12, and 2, it is 40. How many atoms of oxygen and chlorine should be bonded to silicon to be saturated? Silicon has 4 valence electrons, it is not saturated. It needs 4 other electrons to satisfy its octet rule. If we make a bond between silicon and oxygen, oxygen has 6 valence electron and chlorine has 7 valence electron. So silicon with 4 valence electron should be bonded to 2 oxygen atoms in order to be saturated. And since the chlorine atom has 7 valence electron, it needs 1 more electron to be saturated, so silicon can be bonded to 4 atoms of Cl. According to Vesper, how can we write the geometrical shape of silicon oxide? According to Vesper, the rule is Ax and Em. X is the number of atoms bonded to the central atom, which is Si. In case of Si2, we have two oxygen atoms bonded to Si. So, the rule is Ax2. E is the number of lone pairs on the central atom. Si has no lone pairs since it is the loose dot structure of SO2 is as follows. So Si has no lone pairs. So E is 0. According to Vesper, it is Ax2. Since it is Ax2, it is linear. The geometrical shape is linear. Silicon exists in nature as a mixture of three isotopes, which are given in this table, but the mass number of the first isotope and the mass number of the third isotope are unknown. To calculate A and A1, which are the mass number of Si with percentage 90% and A1 is the mass number of Si with percentage 4%, we have two relations. N plus N1 equals 31. What does this relation mean? N is the number of neutrons of Si21 and N1 is the number of neutrons of Si with mass number A1. But we know that silicon atom has atomic number equal Z14, and all the isotopes have same atomic number. So for Si29, its number of neutron is equal to A minus Z. It is equal 29 minus 14. It is equal to 15. For Si with mass number A1, N1 equal A1 minus Z. It is equal to A1 minus 14 since A1 is unknown. By adding the two number of neutrons according to the relation above, it is equal to 31. N is 15 plus A1 minus 14 equal 31. So A1 equal to 30. To find A, we have this relation. A1 equal A plus 2. So A equal 30 minus 2. It is equal to 28. To calculate the average atomic mass, according to the rule, average atomic mass equal percentage times summation of the percentage times atomic mass over 100. For the first isotope, the percentage is 90. The molar mass or the mass number of Si, A is calculated. It is 28 plus percentage times mass number of the second isotope. It is 29 plus percentage is 4 times mass number of the third isotope. It is A1. It is equal to 30 over 100. By calculation, the average atomic mass is equal to 28.14%. Sorry, The third exercise in the biweekly worksheet 2, it is about magnesium. We have a certain introduction about magnesium, and this magnesium is present in many kinds of food. It can be presented in milk, in water, in chocolate, and other types of food. If we take 100 grams of milk, it contains 60 milligrams of magnesium. If we take a certain type of water, in 100 milliliter of this water, we have 10 to the power minus 4 mole of magnesium. How can we get the amount of magnesium in milligram? Amount of magnesium in milligrams, so we have to find mass. Mass equal number of mole times molar mass. Number of mole is 10 to the power minus 4. Molar mass of magnesium is given in this exercise. It is 24. So it is 24 times 10 to the power minus 4 gram. But to change from a gram into milligram, we know that 100 milligram equal 1 gram equal 1000 milligram. So we multiply by 1000 to get 2.4 milligram. this type of water, 100 milliliter of this type of water contains 2.4 milligram of magnesium. If a mother is preparing for her child milk by using this type of water, she puts 2 spoons of milk. Each spoon has 11 gram and in a bottle of 100 milliliter of water. How can we calculate the amount of magnesium obtained from milk alone? We have to calculate the mass of magnesium which is obtained from milk only. In each spoon of milk, one spoon of milk weighs 11 gram. So 2 spoons of milk has 22 gram. The mass of 2 spoons of milk is 22 gram. And from the table we know that 100 gram of milk contains 60 milligram of magnesium. The mother used 2 spoons of milk. The mass of these 2 spoons is 22 gram. So 22 gram of milk contain how many grams of magnesium? By calculation, mass of magnesium in milk used by the mother is equal to 22 times 60 over 100. It is equal to 13.2 milligram. So when the mother used 2 spoons of milk, the amount of magnesium in this quantity of milk is 13.2 milligram of magnesium. For part 2, how can we calculate the mass total of magnesium in this bottle of milk? In this bottle of milk, the mother puts 2 spoons of milk and 100 milliliter water. In these 2 spoons of milk, the amount of magnesium is 13.2 gram. In 100 milliliter water, the amount of magnesium is 2.4 gram. It is calculated in part 1. So by adding the 2 quantities, we can get the mass total of magnesium in this bottle. It is 15.6 milligram. From the part above, we deduced that in a bottle of milk containing 100 milliliter water and 2 spoons of milk, this bottle contains 15.6 milligram of magnesium. If a child took only 1 bottle of this milk, we have to specify if the quantity of magnesium taken satisfy his daily need. For children, the daily need required is between 100 and 400 milligram per day. If this child took only 1 bottle of milk, so the quantity of magnesium taken is 15.6 milligram, where 15.6 milligram is less than the minimum daily need, which is 100 milligram. So this quantity of magnesium is insufficient. So how can we calculate the number of bottles of milk needed to satisfy his daily need? In each bottle of milk, the amount of magnesium is 15.6 milligram. The minimum daily need is 100 milligram for a child. So how many bottles should he take to satisfy his daily need? By calculation, we get the number of bottles equal 100 times 1 over 15.6. It is equal 6.41 bottle. So at least this child should take 6.5 bottles of milk to to satisfy the minimum daily need of magnesium.